All right, so you probably think of functions as simple little machines, right? You put one thing in and you get another thing out. Easy enough. But what if you could actually chain those machines together? Imagine feeding the output of one directly into the input of the next. Suddenly, you can model some really complex systems. That's the incredible power of composite functions, and we're about to break down exactly how it works.
So let's start with that big question right there. We know a function takes an input and transforms it. But what happens when that output doesn't just stop? What if it immediately becomes the starting point for a second function? That's the puzzle we're going to solve today.
To get our heads around this, we first need to give it a name. When we chain these function machines together, we're creating what's called a composite function. Think of it like a little assembly line, where what comes out of one station goes directly into the next.
Now, check out that notation. F of g of x. It literally means f of g of x. It's like a chain reaction. The output from function g becomes the direct input for function f. And what you get at the very end is a brand new single function that does the work of both. It's pretty cool.
I know f of g of x can look a little abstract, so let's make this way more concrete with a really simple analogy. Forget numbers for a second, and let's think about family relationships.
Okay, so let's say we have a relationship from a son to his father. That's our first function. Then we have another one from the father to the grandfather. That's our second function. So what's the composite function? It's the shortcut. It creates a direct link to finding the son's relationship to his grandfather. See how it connects the beginning of the chain straight to the end?
All right, analogies are great, but how do we actually calculate this stuff? Let's get our hands dirty and look at the mechanics. Now, the key rule, and you're going to hear me say this a lot, is that you always solve from the inside out.
So, for our big example, we're going to be working with these two functions right here. We've got f of x, which is 5x plus 2, and we've got g of x, which is 2x squared minus 3. Our first mission is to combine them to find f of g of x.
Here is our game plan, and it all comes back to that inside-out rule. In step 2, you see we find the inner function, g of x. Then, in step 3, and this is the magic move, we take that entire expression and substitute it into the outer function, f of x. This is the exact moment where the two functions really combine.
And this right here is the whole ball game. Look at our f of x function, 5x plus 2. To find f of g of x, we're literally going to take out that x and replace it with the whole block that is g of x. So our new expression becomes 5 times 2x squared minus 3 plus 2.
And now for the easy part. Just simplifying, we distribute that 5 to get 10x squared minus 15. Then we combine the numbers, negative 15 and positive 2, and there it is. Our shiny new composite function is 10x squared minus 13. We did it!
So we've figured out f of g of x. But, this brings up a really important question. What would happen if we just swapped the order? Is putting g inside f the same as putting f inside g? Well, let's find out. Whoa, okay, just look at this comparison. On the left is the answer we just got for f of g of x. On the right is what happens when we calculate g of f of x. For that one, we did the process in reverse. We plugged the f of x expression into the x in g of x. And you can see the results aren't just a little different, they are dramatically different.
So, the takeaway here is crystal clear. Order absolutely matters. Composite functions are not commutative. That's just a fancy way of saying you can't swap them around whenever you feel like it. F of g of x is its own unique machine, and g of f of x is a completely different one, period.
So what happens if we get a little weird with it? What if we compose a function with itself? You'll see this written as f squared of x, which is just a shorthand for f of x. Let's take a look.
The logic is exactly the same as before. For f of f, we plug 5x plus 2 back into itself. For g of g, we do the same with 2x squared minus 3. And just look at the result for g squared. By combining a pretty simple function with itself, we've created a much more complex one.
Okay, we've covered a lot of ground, from grandfathers to function assembly lines. So let's boil all of this down into the 3 key rules you absolutely need to walk away with from this explainer.
All right, here they are, the 3 golden rules. Rule 1. Where do you start? Always, always from the inside out. Rule 2. What's the main move? It's all about substitution. You're replacing the x in the outer function. And rule 3. Can you swap the order? Nope, almost never.
Remember these three things, and you've basically mastered the core idea of composite functions.
And that pretty much brings us to the end. We've seen how you can chain these simple machines together to create new, more powerful ones. So, I'll leave you with a final thought. Now that you have this tool in your toolbox, what's the most interesting or complex function change you can possibly dream up?